Alright, so we're talking about area and definite integrals, and this is going to be part one in the series. Okay, but area and definite integrals is taking a look at a shape that looks something like this and then finding the actual area of this shape. Now, the area of this shape is this area in here. Okay, so this area in here. Alright, that's what I'm talking about. Let me get rid of it so we don't have to deal with it anymore. Okay, so what we're going to do is think about, okay, if we could make it up of a bunch of shapes we know, we could actually work with it. Now, this area is between 1 and 2. Okay, so I'm going to draw a halfway point. This is going to be 1.5, and I'm going to draw an actual triangle or point up to here. Okay, all right, so this is just what we're working with right here. So what we could do, this could be, we could make some rectangles out of these two areas and find that area. Now we can make the rectangle actually have its beginning point beyond this point. We call that the lower bound. Okay, so we call that the lower bound rectangle. Okay, and what we do is find the area of each of these rectangles, and we find the height and the width of this first rectangle, and then we multiply them to get the area. And then we do the same thing here, except we're going to have another height, a different height. We'll call this height 2. And we'll keep, since these are both the same widths, we just keep the same. We find that area, and this is area 2. Okay, and we add these two areas together and we have the actual area underneath. Now obviously it's an approximation because we're actually missing this part. Okay, alright, so let's get rid of those. Okay, and then I'm going to take a look at these right here. I'm going to get rid of those real fast. Alright, so that's a lower bound. So we're underestimating on that one. Now let's say we want to overestimate. So if we overestimate, we'll go with what is called the upper bound. Okay, we actually deal with this one. Okay, and we do the exact same thing. So we call that the upper bound. So in other words, we find the heights, we times them by their widths, we add up how many triangles we got, and we just work with it that way. Okay, and so we could actually find that, but that would be an overestimate. So this is an under, and this is an over. Okay, so something pretty simple as that. Alright, so we have that spot right there. Alright, so now when we're looking at this stuff, it's just, now that we know what we're doing and we're just working with it, wouldn't it be nicer if we had more triangles? Or, I'm sorry, not more triangles, but more rectangles. So let's split it in half again. So let's take the halfway point. Okay, and let's use more rectangles. Okay, so let's use lower bound right here. Look at that, we go a little bit over, and now we're eliminating even more of the gap. I wonder if we added even more. Okay, right? And I'll actually go to Desmos and show you a really cool little thing that will show you something like that. So what we're doing is we're taking some irregular shapes, some irregular shapes, and we're finding the area by populating them with shapes we do know, and we know that it's going to be an estimate and everything. Okay, so let's go to Desmos. Okay, now I'm going to decrease. There we go. Let's go down to, there we go. Okay, so let's say we were looking at this shape and we wanted to find the area under the curve from 0 to, I believe this is 13. Okay, now obviously we're overestimating here with this rectangle, and just imagine that these are just really compacted, or they're not exact rectangles, but just pretend they are for the sake of this argument. Okay, so this is a lower bound estimation, okay, and it's called actually a left-hand estimation because you're on the left side. Okay, all right. So when we take a look at it, this area that this missed is almost made up by this area that is overestimated. Okay, this area and this area underestimated, almost made up by this one, but not as much. So if I increase the number of rectangles you can see that area that's overestimated and underestimated is actually getting smaller and smaller. And if I was able to increase it quite a bit, let's make it, now let's not go too big, let's not go to 100 yet, let's go to 50. There we go. Okay, so if I increase it to 50, you can see that area getting smaller and smaller and smaller, and this getting closer and closer. Now obviously all my functions have really kind of shrunk, so let's just change that to 16. Okay, so we're at 16. Alright, so as I add more and more rectangles, obviously I'm going to have to add them up and just work with them. But obviously at the same time, I'm actually getting closer and closer to having it. Like these two parts right here that I underestimate are almost made up by these 3 parts that I overestimated. And these 4 parts that I underestimated are almost made up by these 2 parts overestimated. But not quite. It's getting to be approximation. Now, let's say I did a right-handed one. Okay, now this is an upper bound. Okay, and once again it does the same thing. Now this one seems to be a lot closer. There's a lot of less underestimation and there's more overestimation. Okay, now some people are probably asking, well, Mr. Vanny, why don't you try a midpoint estimation? Okay, in other words, what if the triangle's right in the middle? Well, right in the middle you can see this almost makes up for this, this almost makes up for this, and this one's really darn close. This one's really close to it. Okay, so you can see a midpoint estimation is pretty close. It's actually really cool how it works and everything. So as you can see, the more rectangles we get, the closer it does get to it. And when we get to a midpoint where we actually have the middle of the rectangle be a point on the curve, it actually comes really close. Well, some of you guys are probably asking yourself, why not try to go to infinity? And we'll answer that in a little sec. Alright, so talking about this, we found that the lower bound rectangle was an underestimate, the upper bound was an overestimate, and we found the midpoint was a closer estimate. Okay, so that was kind of nice to actually see. So that was nice. But once again, it's an estimate. Now, if we thought about it in terms of a sum or a series or a finite series, okay, we would write it with the sigma notation with n over I equals 1. We would start at the first rectangle and work up to the nth rectangle, and we would find the height and width of each rectangle and just add them up and just work with them. It's really kind of cool how that works. Okay. Now here's the thing though, is that with this, while working with this stuff, you guys, you need to understand is we're just looking at rectangles and just working with them. Later on we'll learn some different techniques that actually work a lot better than rectangles, but basically this question started out with how could I find the area underneath this and just be able to work with it. Okay, so it just happens to be that way. Now, obviously, the more and more rectangles, the better off you're going to be. So the bigger this n number is, the larger number of rectangles you're going to have, and the closer your estimate's going to be, but it's not going to be exact. So what we're going to talk about next time is we're going to talk about what happens when you get really close, as in infinitely close. Okay? All right. That's it for today. I will talk to you guys later about area and definite integrals, but just remember, now, there was something in the book that talked about something called the Riemann sums. Okay, now Riemann sums are, what if we get these to be infinitely small, these widths, so that we have an infinite amount of triangles to fit in this one area. Okay, and we'll definitely be talking more about that next time.